This is a KVS Jet bonus were presents. Part 2. This is the diagram of the earth magnetism, and this picture shows about the magnetic field lines of a straight conductor and the circular coil. The next, this picture shows about the overstead experiment. A wire is joined with this battery and a magnetic compass is kept under it. If the magnetic field get deflection, that means there is a magnetic field around the current carrying conductor. That is called overstead experiment. What are the learning units we are going to see now is that number 1, torque on a magnetic dipole, that is Bohr magnet, in a uniform magnetic field. Then earth magnetic field and magnetic elements. Then Bohr magnet as an equivalent solenoid magnetic field lines. Then para, dia and ferromagnetic substances with examples. Then electromagnets and factor affecting their strengths. At last, permanent magnets. Friends, can you tell about this diagram? A copper wire is winded over the nail and joined with the battery. Can you guess what is that? Will be, yes, exactly, it is a setup of the magnetic, that is electromagnet, making an electromagnet. What is electromagnet? Electromagnets are made out of a coil of wire, that is wire curled in series. This is more effective in producing a magnetic field than just a wire running straight. This effect can be strengthened by winding a wire tightly around a powerful core made of magnetic material such as iron. The picture above shows a coil wound around an iron nail. On its own, the iron nail's god is not magnetic. Properties of this magnet. A few properties of the magnet are as follows. That is attractive property. Ferromagnetic materials like iron, nickel and cobalt are attractive by magnets. And repulsive property, like poles repulse each other while the unlike poles attract each other. Repulsive property, like poles as I told you just now. Then directive property, a freely suspended magnet always points the north-south direction. Working principle of electromagnet. So, how do magnet works? Let's consider the iron nail itself. Why does it produce a magnetic field when not influenced by an electric field? Then factors affecting the strength of magnetic field. Dear friends, you can observe this diagram. What are the, first of all, things are there. First one is nail, then battery cell, then switch, then pins. And the setup is called electromagnet. That is, a copper wire is winded over the nail. So when a battery is joined with that, the current will flow through, and when the current going through this coil will produce a magnetic field. So when it attracted the pins, you can understand this become a magnet. It is a temporary magnet and magnetized due to the passing current, so called electromagnet. Magnitude of current carries by. The higher the current, the higher the strength of magnetic field. Yes, how much current we are giving to the nail, that much amount of the strength of magnet field will be increasing or decreasing. So this is one of the factor affecting the strength of the magnetic field of electromagnet. Then second, number of turns. Yes, if the number of turns are increasing, the magnetic field also will be increased. The greater the number of turns, the greater the strength of magnetic field. Then soft iron core. Soft iron core helps to concentrate the magnetic field lines to produce a strong magnetic field. Example, alcino. It's one of the material which is a soft iron core can increase the magnetic field or magnetic strength of the electromagnet. And the next topic is that here you could guess that this in the shape just like a electric field. Here in North Pole, South Pole, a bar magnet is kept in the influence of the North and South Pole, then which is in the uniform magnetic field. This bar magnet tend to rotate because the force acting on the South Pole and North Pole both are equal and opposite that cancel each other. Therefore, net force will be 0. Then the bar magnet tends to rotate. Let us go through this. Torque means a coupling effect. When the forces become 0, then the torque will acting on the system. So torque acting on a bar magnet in uniform magnetic field. The force experienced by the North Pole is equal to mb. That is Q is nothing but here the mentioned Qm means the magnetic poles mb. B is a magnetic field vector. The force experienced by the South Pole will be similarly Fs is equal to minus Qm B vector. The next, the total force will be sum of the North Pole and South Pole force, that net force is equal to 0. Both are opposite to each other. The moment of force or the torque experienced by the North and South Pole about the point O is tau is equal to On vector cross Fn plus Os cross Fs. Then tau On vector cross Qmb plus Os vector into minus Qmb. Then torque is equal to L into Qb sin theta plus L into Qmb sin theta. Since the sin theta both are equal, then it will be added up. So 2L Qmb sin theta. We know that 2L Qm will be the magnetic moment of the magnetic field. So that is written here, Qm into L is equal to the magnetic moment of the bar magnet. So therefore the torque experienced by this magnetic bar magnet kept in the uniform magnetic field is tau is equal to Pmb sin theta. So in vector form, tau vector is equal to P cross B, that is a magnetic moment of the magnet into the magnetic field vector. The next, the potential energy of a bar magnet in a uniform magnetic field. Potential energy is nothing but how much work is done to rotate this or taking the torque. So that amount is nothing but called potential energy of the bar magnet. If the dipole is rotated through a very small angular displacement d theta against the torque tau at the constant angular velocity, then the work done by the external torque B is small angular displacement is given by tau B is equal to modulus of the dipole moment and the magnetic field vector, then sin theta. You know that theta is angle between the bar magnet and the field. Then the small work done to rotate this bar magnet, tau external into d theta, just modulus. The bar magnet has to be moved at a constant angular velocity, which implies that tau modulus of tau is equal to modulus of external. That the small work done is equal to Pm B sin theta into d theta. Then total work done in rotating the dipole from Q dash to Q, that is full rotation. Then it's a small work done. If I take integration, then the total work done will be coming. Then work done is equal to integration of theta dash to theta, then tau into d theta, which is equal to theta dash to theta limits the Pmb sin theta and d theta. When sin theta and d theta will be minus cos theta, the put the limits theta dash and theta. Then work done is equal to minus Pm b common, then cos theta minus cos theta, that will be cancelled. Then you will be taking potential energy is equal to minus Pm into b cos theta minus cos theta dash. Then it is nothing but if the cos theta is equal to 0 is equal to 1, then potential energy is equal to minus Pm V cos theta. That is magnetic moment and the magnetic field and the cos theta. Minus symbol shows that in the opposite direction. Therefore, the potential energy of the Bohr magnet in the uniform magnetic field will be U is equal to minus Pm vector dot B vector. When cos theta remove, then will become dot product. And this is the direction of the Curie-Swain's law, susceptibility versus temperature. So the temperature dependent of the magnetic field according to magnetic substances, the properties of the magnet. First one, magnetizing field. The magnetic field which is used to magnetize a sample or specimen is called the magnetizing field. Magnetizing field is a vector quantity and it is denoted by H vector and its unit is ampere per meter. Then magnetic permeability. The magnetic permeability can be defined as the measure of ability of the material to allow the pass of magnetic field lines through it or measure the capacity of the substance to take magnetization or the degree of penetration of magnetic field through the substance. Then relative permeability mu r is defined as the ratio between absolute permeability of the medium to the permeability of the free space. So that mu r, that is relative permeability, is equal to the permeability of the medium divided by permeability in the vacuum. So it is given by the m vector is equal to magnetic moment by volume 1 by V, sorry, I by V into Pm. Then magnetism is equal to magnetic moment divided by volume. Qm 2L by 2La and 2L 2L cancel, the remaining will be get Qm by A. So the modulus of magnitude of the magnet will be Qm into 2L, then divided by 2L into A, 2L cancel Qm by A. So this means the Bohr magnet, for a Bohr magnet, the intensity of magnetization can be defined as the pole strength per unit area. So m by small m by A, you can say that capital M is equal to small m by A, that is called a poles per unit area is called the intensity of the magnetization. Then the magnetic field can be summed as the magnetic field in the vacuum plus in the medium, which is called mu naught H plus mu naught I. I mean intensity, H means magnetization. Then B vector is equal to B naught plus Bm, that is called mu naught into total H plus I. Next, magnetic susceptibility. The symbol is chi m is magnetic susceptibility, that is the modulus of the magnetization divided by the modulus of the magnetic field. Then chi m can be written as C by, in case of the temperature, C divided by C minus Tc, that is Curie-Swain's law. According to that, the susceptibility versus temperature, we can write this relation is called the Curie-Swain's law. And now you are viewing the type of magnetism and magnetizing field strength H absent, the magnetizing field present, and magnetization of the material, susceptibility, relative permeability. According to the dia, para and ferromagnetism. There are three types of the magnetic materials. They are classified into dia, para and magnetism, ferromagnetics. So these are diagram, zero magnetic moment, and here aligned opposite to the field. When the field is applied to it, is magnetic opposite to the direction of the magnetic field, and here aligned with the field, same direction of the magnetic field, and here also that is a little more not improper, and next aligned with the field, that is magnetizing field. The next magnetization of the material versus M versus H, magnetic field and magnetization. So this is a little decreasing order, this is increasing order, and this is increasing and then constant. Susceptibility in this case is negative, first case, diamagnetic magnetism, and para by positive and small, and ferromagnetic positive and large. Relative permittivity in case of the dia less than 1 and is greater than 1, second one, and ferromagnetic very large. So the magnetism or the earth magnetism is the branch of physics which deals with the earth magnetic field is called the geomagnetism or terrestrials. Terrestrial means earth only, terrestrial magnetism. So that study about the earth magnetism can be called as the geomagnetism or terrestrial magnetism. So earth magnetic field and the earth elements are shown in this diagram. This is the earth and its magnetic. The geographical north is the magnetic south, and magnetic south is the geographical north. It's written here. And this is the diagram which representation magnetic inclination, horizontal magnetic field, north geographical mid, magnetic pole, and the lines of magnetic force, dip, needle, and the magnetic equator and the equator. So there are the quantities required to specify the magnetic field of the earth on its surface, which are often called as elements of the earth magnetic field. They are magnetic declination, symbol D, magnetic dip or inclination I, and the component of the earth magnetic field BH, that is horizontal magnetic moment of the earth magnetic field. Then this diagram shows about this, the first one, the same case. The true north pole, the earth rotates around this axis. This is the earth considered to be. Magnetic north pole, magnetic lines of field, just like first one I told you, here the magnetic south pole and the true south pole. Geographical meridian, and D is the angle of incident, and this is the geographical meridian in case of the compass needle, and magnetic meridian. And next, this is earth that is inclined by 70 degree. This is the magnetic equatorial, and this is geographical meridian, magnetic meridian, and geographical equator. So by this diagram, rectangle, you can see that this is the angle between this magnetic meridian and the geographical meridian. That is called the angle of declination. That is nothing but called a dip. Then needle of magnetic compass rests vertically at an angle of dip at magnetic poles. The angle between the magnetic meridian at a point and the geographical meridian is called the declination or the magnetic declination D. The angle subtended by the earth total magnetic field with the horizontal direction in the magnetic meridian is called the dip or magnetic inclination. The component of earth magnetic field along the horizontal declination, the magnetic meridian, is called horizontal component of the earth magnetic field, denoted by B. So this is the same diagram which I explained the previous one. And in case of the diagrammatic representation for the geographical meridian, this one, and this frame is magnetic meridian, vertical plane parallel to the magnetic axis. So this B means vertical magnetic field and H means horizontal magnetic field. In between these two angle is dip and the next one we can go comparison of the magnetic substances. I know that there are the three types of magnetic substances, dia, para and ferro. First one is diamagnetic substances are those substances which are feebly repelled by the magnet. Example, antimony, bismuth, copper, coal, gold, silver, quartz, mercury, alcohol, water, hydrogen, air, argon, etc. Then para, paramagnetic substances are those substances which are feebly attracted by the magnet. Example: aluminum, chromium, alkali and alkaline earth metals, platinum, oxygen, etc. Next, the ferromagnetic substances. Ferro substances are those substances which are strongly attracted by the magnet. Example: iron, cobalt, nickel, gadolinium, dysprosium, etc. Then second point will be when a magnetic substance is placed in the magnetic field, the lines of force tend to avoid the substance, so going out of this. So the lines of force prefer to pass through the substance rather than air in the para substance. See that? Passing through. And next, the lines force tend to crowd into the specimens in the case of ferromagnetic substances. And third will be the diamagnetic substances. A rod is feebly suspended in uniform magnetic field. It aligns itself in the direction of the perpendicular to the field. The direction source is perpendicular. When a paramagnetic substances or the rod is freely suspended in a uniform magnetic field, it aligns them itself a direction parallel to the field. Parallel. When a paramagnetic substances rod is feebly suspended in a uniform magnetic field, it aligns itself in the direction of the parallel to the field very quickly. So both is the case, ferro or both are alike. Then comparison goes on the four substances. If diamagnetic liquid taken in a watch glass placed in a uniform magnetic field, it collects away from the center when the magnetic poles are closer to the, and collects at the center when the magnetic poles are farther. See, this is the magnetic substances. When you kept in the watch glass, the liquid, it doesn't take inside. When it's moving apart, this is closer, moving apart, elevation takes place. Similarly, in the case of the paramagnetic liquids, when it is closer, the substance will be just opposite to the second one of the diamagnetic. So this is paramagnetic substance. The paramagnetic liquid substance kept in this far away, a depression take place, just opposite to the diamagnetic liquids. And the ferromagnetic liquids kept in the watch glass and depression, elevation take place. So in this case, para and ferro both are same. So that if ferromagnetic liquids are taken in watch glass is placed in a uniform magnetic field, it collects at the center when the magnetic poles are closer and collects away from the center when the magnetic poles are farther. So by seeing this diagram, you can understand, you can even write what is the nature of the substances. And this is a permanent magnet and a temporary magnet. You can observe this electromagnet and this is a bar magnet. Permanent magnet and electromagnets. Let us see the features permanent magnet in case of that electromagnet. What is it? Permanent magnets means substances which retain ferromagnetic property for a long time at the room temperature. But in case of the electromagnet, but temporarily it will be there. In a day-to-day applications, we need electromagnetic which are again made of paramagnetic materials, electric bells, loudspeaker, telephone, diaphragm, grains, etc. Use of electromagnets. And the second point, electromagnet, soft iron and the steel alloy can be used for that. Here the steel, alico, cobalt, steel and the declination all are the permanent magnets. That is substances. How can made? One of the method duplicated 400 years old back is hold an iron rod in north or south direction and hammer it repeatedly. Hold a steel rod and stoke it the one of the bar magnet and many times always in some direction. Place the ferromagnetic substance rod in a solenoid and pass current the magnetic field in the solenoid magnet. Issue the rod. And here the places the soft rod in a solenoid and pass the current, then it becomes electromagnet. And in case of the properties of this permanent and the electromagnet, first permanent magnet is high retentivity. For the magnetic to be strong. The second, temporary fluctuation, minor mechanical action, and the stray magnetic fields nearby should not be introduce the magnetic effect of the magnet. High permeability it has. But in the case of this electromagnet, high permeability, low retentivity, narrow exchange curve, and energy dissipation is very small, high resistivity take place. And the next we can conclude the summary of the what we have learned. Torque on a bar magnet, magnetic dipole in a uniform magnetic field, earth magnetic field, bar magnet as a equivalent solenoid, magnetic field lines, diapir and ferromagnetic substances with the examples, electromagnets and factors affecting their strength, and permanent magnets. Thank you for watching this watching this PPT. Then you can understand the